Who will speak to us on the Z-Dirac and massive Laplacian operators in the Z-invariant Ising model. Thank you.
Thank you. So first of all, I would like to thank the organizers for the opportunity to speak here. I'm very glad to be here. It's been really interesting. So today I will tell you how the Z-Dirac and the massive Laplacian operators are kind of intertwined in the Z-invariant Ising model. So actually this question arose quite a long time ago. And the reason is the following. So the Z-Dirac, if you look from the point of view of statistical mechanics, the Dirac operator and the Laplacian operator are related to spanning trees and spanning forests. So, and spanning trees are usually a model that is simpler than the Ising model, so it's kind of interesting to understand if the two are related. And then the second reason is that the Dirac operator and the Laplacian operator yield to the notion of holomorphic functions and harmonic functions, which played a big role in the proof of conformal invariance of the Ising model at criticality. So I kind of wanted to understand how all of this is related. So the plan of the talk is the following. So there's a lot of building up. So first I will tell you about isoradial graphs. So you've seen the definition in Martin's talk, but I'll repeat it. Then I will tell you about the Z-invariant Ising model, which has been introduced by Baxter, and also about Fisher's correspondence, which is the tool that I use to study this Ising model. Then I will tell you about the Z-invariant massive Laplacian operator that we have introduced with Cédric Boutier and Kylian Rachel. Then I will tell you about the ZU-Dirac operators, which is a family of operators, which was one of the missing pieces in the non-critical case. And then I will tell you about results, finally, how all of these connect. Okay, so a graph is isoradial if it is planar and can be embedded in the plane in such a way that all interfaces are inscribed in a circle of radius 2, so let's take 2, and such that the center of the circles are in the interior of the faces. So isoradial graphs date back quite a long time to Dauphin in the 60s. They were used by Mercat, by many people, and the name isoradial comes from Kenyon. So if you want to construct an isoradial graph and it's together with its dual, you can use a generic way of doing this is to use the rhombus graph, which I will denote by G diamond. So start from a rhombus graph G diamond, and then you partition, so it's a bipartite graph, and so you partition the vertices into bullets and little diamonds in a bipartite way. And then you draw the diagonals of the rhombi. So you have two sets of diagonal, and both of them will be isoradial graphs. Okay, so the primal and the dual. So they're defined up to duality. So all of this works for the full plane and also for simply connected domains. But I will not be careful to tell you about the boundary. So it's quite a lot of work to handle the boundary, but I'll be quite fussy about that. But you can define everything nicely also along the boundary. Okay, and so when you have an isoradial graph, to every edge you can assign a rhombus, so here in yellow. And so using this rhombus, you can assign to every edge an angle, theta e bar with a bar, which is a geometric angle of the embedding, which is a half angle at the edge, well, at the corner of the edge. I think you see it on the picture. So you have the primal angle and the dual angle, which is pi over 2 minus the primal angle. Okay, so this is isoradial graphs and the structure that we will need. Now, the Z-invariant Ising model. So first, the Ising model, you've seen quite a few times the definition. You take a finite graph, we'll take it to be isoradial, but you can think of it as being general planar graph for the moment. And on this graph, we consider the set of spin configurations, meaning plus or minus 1 assigned to each vertex. So I choose to put two colors, blue and green. So on this, you have an example of a spin configuration. Okay, and so in the Z-invariant case, you choose the coupling constants in a specific way. Okay, so they have been computed by Baxter. So the coupling constant of an edge E, you will suppose that it is a function of the angle and of a parameter little k. And it is equal to 1/2 of log of 1 plus Sn theta ek divided by Cn theta ek. So little k is the elliptic modulus. It's a parameter such that actually the real parameter is the square, and the square lives at -∞1. Big K is the complete elliptic integral of the first kind. So you can think of big K as being pi over 2. And Sn and Cn are 2 of the 12 Jacobi elliptic trigonometric functions. And so Sn and Cn is like an elliptic generalization of sine and cosine. Okay, so they're b-periodic meromorphic functions. And theta e is a modification of the geometric angle equal to 2k over pi. So meaning that, okay, well, I'll tell you later about the specific regime. Okay, and so an important point is that as the parameter k squared varies from minus infinity to 1, then the coupling constant varies from 0 to plus infinity. So you recover the whole range of the Ising model. And so you should think of these coupling constants as encoding the interaction intensities and also the external temperature. Okay, so we will not have a beta because the beta is kind of encoded in the k squared, if you want. Okay. And then, so you have specific coupling constants, and then the Ising model is defined as usual. So the energy of the spin configuration is minus the sum over all edges of the coupling constant times the spin at x times the spin at y. And the probability of occurrence of a spin configuration is proportional to exponential minus the energy. And the normalizing constant is known as the partition function. And so these weights are special because they're derived using the assumption of Z-invariance. So what you do is that I will not have time to go into the details of these equations, but you can perform like generic moves, which are star triangle moves, and you ask that the partition function only changes by an overall constant when you do these moves. And this gives you a set of equations, the Yang-Baxter equations, and when Baxter solves them, he recovers the formula that I gave you before with 1/2 log of 1 plus Sn over Cn. So the Z-invariance assumption kind of tells you from a probabilistic point of view that your model should be local in some sense. And so we worked quite a bit with Cédric on this question, first at criticality. So our goal was to find local expressions for observables of the Ising model. And then also we extended our critical result to the full range of the Z-invariant Ising model jointly with Kilian Rachel. Okay, and so there's a specific regime, the critical one when k squared is equal to 0. Then the elliptic trigonometric functions become the usual trigonometric functions, and so you recover the weight je equal 1/2 log 1 plus sine over cosine, which are the weights that you have seen in Marcin's talk. And so in this case, the model is critical, as Marcin has told you, so it's result due to Lee, Duminill-Coppa, and Timazzoni, and lives in the non-periodic case. And also it's been famously proved to be conformally invariant by Charkak and Smirnov in the Z-invariant regime. Okay. So you've seen this picture, I think, 3 times, but what I wanted to emphasize is that how it relates to the parameter k squared. So here on the left, k squared between minus infinity and 0, you have the mixed phase, then critical k equals 0, and then k squared into 0, 1, you have the frozen regime. Now, Fisher's correspondence. So some of you may know it. So you start from the dual graph. So it works for all planar graphs, actually. So you start from the dual graph, and from it you construct the Fisher graph as follows. So at every vertex, you open up every vertex, and then you draw a triangle at the end point of the vertex, and you join these triangles in a circular way. So you can do this for any planar graph. So here, as an example, you have Z2 star, while the dual of Z2 is Z2, and so you have the Fisher graph of Z2. Okay, and what we'll consider on this Fisher graph is the dimer model. So I will define, we haven't seen the dimer model yet, so I will define it. So a dimer configuration of any planar graph is a subset of edges such that each vertex is incident to exactly one edge of the dimer configurations. They're also known as perfect matching in computer science. Okay, so here is an example of a perfect matching of the Fisher graph. And so a nice thing, let me first define the model. And so then you have positive weight on the edges, and then the dimer-Boltzmann measure is defined as follows. So the probability of occurrence of a dimer configuration is proportional to the product over all edges in the perfect matching of the weight of the edge divided by a dimer partition function. So the nice thing about the dimer model is that you have, since Castellane and then Kenyon and many people, you have like an exact way of solving it and computing things using determinants. Okay, and the main tool is the Castellane matrix. So I will tell you, we will see many Castellane matrices, but I think it's the only time where I really define it. So a Castellane matrix, you first have to orient the edges of your graph in a specific way. So in such a way that the cycles, bounding faces, interfaces are clockwise odd, meaning that when you travel around an interface in the clockwise direction, you have an odd number of edges that are co-oriented. So Castellane proved that this is always possible for planar graphs. Then KF will be the Castellane matrix of the Fisher graph, is the corresponding oriented weighted adjacency matrix. So an adjacency matrix is just a matrix whose rows and columns are indexed by the vertices of your graph, and such that non-zero coefficients encode edges. Okay, so in this respect, it's an adjacency matrix. The tilde means that the vertices are adjacent. And then it's weighted because instead of just putting ones, you put the weight of the edge. And then it's oriented because you will have a sign depending on the orientation of the edge. Okay? So this is the definition of the Castellane matrix. And so the founding result of Castellane is that the dimer partition function is equal to the absolute value of the Pfaffian of this matrix. So actually you can write, so the Pfaffian is equal to the square root of the determinant. So it's closely related to a determinant, but mostly it's written as a sum over perfect matching of a signature times a term times the contribution of the perfect matching. So the only problem is that you have, for it to be a partition function, is that you have the signature of the perfect matching coming in. And so the orientation is there to compensate the sign of the signature in order to really have a partition function. And then from this theorem, you can deduce, so this was done by Kenyon in the 90s, an explicit formula for probabilities of subset of edges. So if you consider a subset of edges E1 to En, then the probability of all perfect matching containing this subset of edges is equal to the product of the weight of the edges times the Pfaffian of the inverse Castellane matrix restricted to rows and columns that encode this set of vertices. So this is an n by n matrix where n is the size of 2n by 2n, where n is the number of edges. Okay, and so maybe there's one important point to keep in mind from this slide, is that while the partition function is related to the Pfaffian, which is a square root of a determinant, and that the probabilities are related to the inverse matrix. Okay, so this is kind of the information you're looking for if you want to understand partition functions and probabilities. Okay, so I haven't told you about Fisher's correspondence yet. So you start from an Ising model on a graph G, so I just put Z2, you have the plus and minus ones, the two colors, and then as we have seen in, I think, Martin's talk and other talks as well yesterday morning, you consider the low temperature expansion of the model, meaning that you consider the contours that separate the clusters of plus or minus spins. So this is the famous Kramers-Vanier duality. So this is the low temperature. You can also consider the high temperature expansion, but we can just stick with the low temperature one. So it's not 1-to-1, it's 2-to-1, because if you reverse all the spins, then you get the same the same contour configuration, but that is okay. It's a 2-to-1 correspondence. Then you keep, so the contours, they're polygon contours. The condition is that at every vertex you have even degree. This is the way of characterizing polygon configurations. Now they live on the dual because they were separating the clusters of spins. And Fisher correspondence goes as follows. So you keep, in the Fisher decorated graph, you have the edges of the original graph. So you keep all these edges. And then what Fisher proved is that there is exactly two ways of filling out each decoration in order to have a dimer configuration, independently of the number of edges that arrive at that decoration. Okay, so I will just show you one of the two to the number of dual vertices possibilities of dimer configurations corresponding to the contour configuration, which you can still see underlying it. So it's not one-to-one, but still you see that you can recover all the information about contour configuration in this Fisher representation of the Ising model. And so when you go through all the mappings that I showed you, and that you start from the Z-invariant Ising model coupling constant, you get the following weights for the dimer model, so Sn over 1 plus Cn for the edges arising from the original graph, and 1 for the edges of the decoration. So this is the dimer model that we'll be considering. Okay, now the Z-invariant massive Laplacian. Okay, so you consider an isoradial graph, an elliptic parameter k, and so the massive Laplacian will be defined as usual. What is special is the choice of conductances and coupling constants. So the conductances on the edges are denoted by rho, the masses by m, and so the conductances will be equal to SC of theta e, where SC is Sn over Cn. Okay, so it's what you have to keep in mind is that it's the elliptic version of tangent. And then the mass is equal at a vertex x is equal to the sum over all neighboring vertices of that vertex over function a depending on the angle here of that edge minus the conductances. And while the function a has an explicit form, but it doesn't really matter for this talk, it involves elliptic functions. Okay, and then as usual, the associated massive Laplacian matrix is defined as follows. So it has rows and columns indexed by vertices of the graph. Then for neighboring vertices, you have minus the conductance. And then you also have a diagonal term where you have the mass plus the sum of the conductances over the neighboring vertices. Okay. And so you can see this matrix as an operator acting on complex valued functions defined on vertices of your graph. So it acts as follows. If you have a function f and you evaluate it at a vertex x, it's going to be the sum over all neighboring vertices of the conductance fx minus fx prime plus the mass evaluated at fx. And so a classical definition is that a function is said to be massive discrete harmonic if it is in the kernel of this operator. And the massive Green's function is, well, the inverse of this operator. And so in the specific critical case, when little k is equal to 0, then we have proved with Cédric and Kylian that the mass is 0, and you recover SC as becoming tangent, and so you recover the critical Laplacian that has been introduced by Kenyon in 2002. And well, which was probably present also in earlier work of Ferrand and other people. And of course, the Green's function is also up to a constant defined as this way, the Green's function of the corresponding random walk, which is a killed random walk when k is different than 0. Okay, and now from the point of view of statistical mechanics, this massive Laplacian is connected to rooted spanning forest. So a rooted spanning forest is a subset of edges spanning all vertices of the graph such that each connected component is a rooted tree. So here in purple you have an example of a rooted spanning forest. So here you have one component and the little circles represent the root of each of the components. So they can be reduced to one point, but it has to span all vertices of the graph. And so on this model, the natural measure to consider, given the conductances as masses, is to say that the probability of a rooted spanning forest is equal to the product over all tree components of the mass at the root of the tree times the product of the conductance of the edges of that tree divided by a partition function, the rooted spanning forest partition function. And so the oldest theorem of this talk is the famous Kirchhoff matrix tree theorem, which tells you that the partition function of rooted spanning forest is equal to the determinant of this massive Laplacian. So again, partition function determinant. Well, this time you don't have the square root. Then in the 90s, Burton and Pimentel proved an explicit formula for probabilities of this rooted spanning forest model using the transfer impedance matrix, whose coefficients, so what we will keep in mind for today is that coefficients of this matrix are differences of Green's function. Okay, so given the Green's function, the inverse operator, you know how to compute probabilities. Okay, And so, yeah, it's called the Z-invariant massive Laplacian because the associated model of rooted spanning forest is Z-invariant in the sense of Baxter. Okay, this is hence the name. Now the ZU-Dirac operators. So to define it, I need to introduce yet another graph. So we start from the original picture of the diamond graph, and then this time we draw both of the diagonals on the same graph. To construct the isoradial with this bipartite splitting, 1/2, 1/2, here we construct both the diagonals on the same graph, and we add a white vertex at each of the crossing of the diagonals. Okay? And so in this way you obtain a bipartite graph with black vertices which consist of vertices of your original graph and of the dual, okay, and the white ones are the additional white vertices at the crossing of the diagonals. And the edges of this graph are the half diagonals. Okay, so let me just remove, so here you just have the double graph. So it's a classical graph in all of these theories. Again, let me picture just the rhombus assigned to an edge and to its dual edge, and I will only now show a local picture. So we introduced an additional parameter, so I was quite surprised by this parameter, but anyway, it is there. So it's a parameter which lives in the, so you have, okay, so the elliptic trigonometric functions are defined in a complex torus, which is a C quotiented by 4k over z plus 4ik prime over z. Okay, so k is like pi over 2. So this torus degenerates to a cylinder in the critical case, but in the non-critical case, you have also a period in the other direction, which gives you a torus. And so you take the intersection of this torus with the real line. Okay, so this is this, and you take any parameter, so on this real line of this torus, so it's on a circle. And you set u alpha to be equal to u minus alpha over 2. And so we define a positive weight function on edges of the double graph, which depend on this parameter u. Okay, and the function is defined as follows. So it goes from white vertices to black because, well, we have a bipartite graph. So W is a white vertex, and X denotes a black vertex, which can be of two types, either a primal vertex or a dual one. Okay, and so on primal vertices, well, primal edges, it is equal to, so this elliptic tangent times dn of u alpha times dn of u beta to the square root of all of this. And on the dual edges, it's k prime, so k prime is equal to square root 1 over minus 1 minus k squared times cs, so it's cotangent times n du beta, n du alpha plus 2k, and so I have to tell you who are alpha and beta. So in the isoradial embedding, these are, I told you that the radii of the circle had length 2. So this is a radius of a circle, so it has length 2, so you can, fixing a basis direction, you can associate to every side length of a rhombus an angle, okay, encoding this edge. So if you have an edge like WV, you will have two angles, alpha, two EI alpha bar and EI beta bar, which are the geometric angles, and again the alpha and beta are the modified geometric angles. Okay, and dn, I haven't told you who it is, and well, in the critical regime it's identically equal to 1. Okay, so you don't see it at criticality. So actually at criticality you don't have this dependence in u. And so the associated ZU-Dirac operator is denoted by Ku, K of u, is the bipartite complex weighted Castellane matrix associated to this weight function. Okay, so here we have a bipartite graph. We can associate to it a Castellane matrix, okay, like we did for the Fisher graph. And since it's bipartite, you have this natural partitioning of the vertices between white and black. So what you say is that you only index rows by white ones and columns by black. It suffices. Okay, so this is why it's a bipartite Castellane matrix. And so you have non-zero coefficient for neighboring vertices again, so it's an adjacency matrix. And now you have a complex phase. So I told you about the Castellane orientation, the way that you should orient the edges of your graph for the Fisher graph. But actually there's another, in the bipartite case especially, there's a nice way that dates back to Kuperberg, that instead of putting signs, which kind of you have to keep track of them, you can instead assign phases using the angles like that I defined. Okay, so it's a nice way of encoding the Castellane orientation, which is easier to write out. And okay, well, yeah, that's a nice. And then you have the weight function. Okay, so the weight function C of u that we have defined here. Okay, and so this Castellane matrix, which I refer to the Z-Dirac operator, it maps function defined on black vertices to function defined on white vertices as follows. So if you evaluate it at vertex W here, you have the sum over the four neighboring terms, okay, the non-zero coefficient of your matrix, times the function evaluated at B1, B2, F1, and F2. Okay, so you have, this is how to evaluate any bipartite Castellane matrix actually on this graph at a function defined on black, defining you a function on white. And so quite classically, a function is said to be ZU discrete holomorphic if it's in the kernel of this operator. And so why this name? Because when k is equal to 0, then as I told you, this function dn is identically equal to 1. And you recover that f is discrete holomorphic because you have, this is basically the discrete version of the Cauchy-Riemann equations. Okay, so SC becomes tangent, so you have square root of tangent plus times the difference of the function plus I times cotangent square root. And you recover the Dirac operator that was extensively studied by Kenyon in a paper in Inventiones, but these Cauchy-Riemann equations were already introduced by Duffin and also used by Mercat, and as you know, discrete holomorphic functions played a big role in the proof of conformal invariance. So it's like a Z generalization of this operator for the full regime, this K of U. Now, from the point of view of statistical mechanics, this operator is related to a model of pairs of directed spanning trees, dual directed spanning trees. So if you consider, to define it properly, you need to consider the finite case. So this is a double graph, another picture of a double graph, and you remove one vertex. So this is GDR, means that this vertex is removed. And the outer face, you think of it as being one vertex denoted by O. And so by Temperley's bijection, which has been generalized to directed trees by Kenyon, Prop, and Wilson, you have that dimer configurations of this graph are in one-to-one correspondence. Really, it's really a bijection this time with pairs of dual directed trees on the graph GR and the dual. So how does the bijection work? Remember that on the double graph, edges are half edges, half diagonal edges. So you start from the black, you go to the white, and you prolong it. Every time you have an edge, you add the half edge going from the black to the white. Okay, so for example, for this one, you add this edge. Here we have a dual edge, and we extend it. And so, well, the theorem states that when you do this local procedure, what you get on the right is a pair of dual directed trees. So the pink one is the dual one. It's rooted at the outer vertex, the O. So it looks like a forest, but actually it's a tree because the outer vertex is a single, well, it's a single vertex. And the dual tree, which is in turquoise, is rooted at this vertex R. Okay, so you get a directed tree. Pairs of directed trees. So if you start from a weight function on your dimer half edges, what you get is quite naturally a weight function C tilde on directed edges. So let me emphasize that here the edges in both directions are not the same, okay, because of the definition of C of U as it is. Anyway, in the full, not at criticality, but away from criticality, they really consist of directed trees, meaning that the edge in one direction doesn't have the same weight as the one in the other direction. And so from the Dimer-Boltzmann measure, you naturally get a measure on pairs of trees. And so using the theorem of Kasselin and Kuperberg for the special orientation, you have that this pairs of spanning trees partition function, so G star with this modified weight, is equal to the determinant of this Z-Dirac operator. And using the theorem of Kenyon that I told you, well, the probability measure is expressed using this operator and its inverse, okay, the inverse Dirac operator. Okay. And also, so with this operator, with this special weight function CU, actually those directed spanning trees are Z-invariant as well. It's also a generalization to directed trees of the usual Kirchhoff's law for non-directed ones. Okay, so now results. Okay, so the first theorem says the following. So you consider a Z-invariant Ising model on a finite isoradial graph G with plus boundary conditions. And then you have that for every U in, so this real locus of the torus, there's a prime because we have to remove a few vertices, but okay, essentially for any point on this, you have that the squared Ising partition function is equal up to a constant to this pair of directed spanning trees partition function, and also it's equal up to another constant to this rooted spanning forest partition function. Okay, and so this arises from an equality on determinants of the matrices. Okay, Ising partition function is a Profian, it's square root of determinant, so this is why you have a square when you have an equality between determinants. Okay, so let me comment on this result. There are quite a few comments. So first, the constants are explicit, but I just haven't written them down. So until what time do you have, Scott? What time am I supposed to finish?
What's the official time? I guess about 12:15, yeah.
At 12:15. I have 1 hour. Okay, cool. I know we started at half past. Okay, whatever. Until 12:15.
You can stop anytime.
Okay, no, but that's perfect. Good. I will have time to give you the proof. I'm really happy. Okay.
Just one question. If there was no, where was U on the left?
Yes. So this is one of the comments I want to make. Okay. Okay. So before commenting on the U, let me comment on this equality. So at criticality, those spanning tree pairs are actually non-directed, okay? And the Laplacian is non-massive. So actually it's well, kind of trivial that the two are equal, okay, at criticality, because they count spanning trees using temporalist bijection. You have primal and dual, but you can remove the dual because it's non-directed, so you actually count spanning trees and not pairs of spanning trees. But away from criticality, they're combinatorial objects of quite a different nature, okay? This is, as I told you, pairs of directed trees, and this is rooted spanning forest where you have a root, but the edges are non-directed. So it's not trivial that the two should be equal. So it's part of the theorem comparing the two. Now, the U. This was one of my big problems because, as Bertrand just said, on the left you don't have U, okay? So why? So this means that this is independent of U. And actually the problem is that, well, here the function depends on U everywhere, at every edge, so it's really difficult to see why this should not depend on U, not knowing this. Now, for the rooted spanning forest, when I defined it, remember that on the edges you have the SC of theta, and you have the mass, and there was no dependence in U, actually, for the massive Laplacian. So why did I put a U here? Because when you handle the simply connected domains, there is a dependence in U along the boundary only. Okay, so this little partial sign here denotes boundary. It means that for Ising you really have to tune the boundary very carefully, and so that you still have, even in this massive Laplacian, you still have a dependence in U along the boundary. Okay, so they're rooted spanning trees with this U on the boundary. And so you want to know, well, why does this not depend on U? And actually, honestly, it's really difficult to see. And it's only when I had the second proof, completely different, that I was convinced that it was true. And when you see the second proof, then it's maybe, it roots in the fact that you have trigonometric or elliptic trigonometric identities and that you can have a free parameter that kind of cancels out. But once you do all the combinatorics, it's really difficult to see that it evaporates.
But then if you take special limits, you find special identities which tell you something which you didn't know before. If you take various limits in U, for instance.
Well, yeah, so U oscillates, it's kind of defined on a circle. So I'm not sure, you can take special values which will kind of root your thing in a different way. You will see also when we go to the inverse, okay? So they're quite specific things happening, but I'm not sure that for the partition function it will tell you, well, it will give you huge identities that are probably not known, but then they will not maybe tell you something about the Ising model specifically. But you will see for the inverse it really plays a big role. You have to fix U, so then you see different things. Okay, so the history of this result. So for the second equality, we have a similar result with Cédric, first in the toric case, when your graph is embedded in the torus. So first with Cédric in the critical case, and then we extended this with the Cédric and Kylian in the general Z-invariant case. The problem with this proof is that it's an abstract argument, it's a 5-line proof, and there's no way of extending it to simply connected domains, okay? It uses specific things of the parameterization of an elliptic curve, and well, so it's really a specific argument related to the periodic, to the torus case. So this was actually already, well, actually 3 years ago, I wanted to understand already, because from the combinatorial point of view, these two things count very different objects. So I worked quite a bit in understanding how the combinatorics of the two are related. And actually 3 years ago, I presented one of the combinatorics proof I had for this identity at criticality. Okay, and since then, well, things moved on. So I have two different combinatorial proofs of this fact, which actually extend to the massive case, but this is not the proof that I have done in this paper. The problems of these combinatorial proofs, I kind of like them, but that you cannot go to inverse matrix, and that our final goal was to understand probabilities. Partition functions are nice, but what you want to understand in the end is also probabilities. And going to inverse with combinatorics was too difficult. Okay, and then the next theorem tells you what happens for inverse matrices, so for probabilities. So you consider a Z-invariant Ising model on an infinite isoradial graph. So I'm stating the result in the infinite case, but I also have a version for the finite case. So it really resembles, but you have another term which is a boundary term, okay? And so F dimer is the dimer-Moulton measure on the Fisher graph, and Kf, this is just a reminder, is the associated Catalan matrix. So this is not part of the theorem, it's just a reminder. Well, I told you the theorem in the finite case, that the probability of edge configuration could be computed using the Catalan operator and its inverse. This also holds in the full plane, and this is due to, so it dates back to Cohen, Kenyon, and Prof to take the weak limits. Then it's been generalized to the bipartite case by Kenyon, Okunkov, and Sheffield. And then, so in this non-bipartite case, because the Fisher graph is non-bipartite, you needed a more robust argument because there was a thing about, you needed a more robust argument. And so this is what we had done with Cédric in our first critical Ising paper. So you have such a formula that holds. And so what is in this statement is that the inverse coefficients, so they're split into three. You'll see on the next slide how they are split. It's actually, I'm using Dubéda's notation. You have three types of coefficients, but the important point you have is that each of the coefficients can be written up to a constant term as a linear combination of two of the Z-Dirac operator for well-chosen values of u. This time I'm fixing the u. You see, before we had a general u. When you want to extract a coefficient, you have to choose specifically the u. I will show you on the next slide how this works. And then you have as a function of the Z-Dirac operator, and also directly using the Green's function. Okay, and so all of them, well, this one is just you compute it from the other ones, but so the two of them has this general same flavor of being sum of Dirac operators, inverse Dirac, or Green's function. And so an interesting point is that, for example, at criticality, dn is equal to 1 and k prime is equal to 1. So you just have like a derivative. Well, this is actually known by Kenyon, as you will see, but then you just have a derivative of the Green's function. Okay. So let me show you just one of the formulas a bit more in details. It's just to tell you don't need to record all the notation, but it's just to tell you that actually all the terms are local in the sense that they depend on the starting point that I write with an underline and on the ending point, which is an A, which is here. Okay, and so Dubeda had this nice way of splitting the vertices. The A ones are inside the decorations and the B ones are neighboring the edges of the original graph. And so the F here stands for final, so beta F is an angle here in the final on the arrival point, and I stands for initial, so it means that it's an angle at the initial point. Okay, and as I told you, you have a similar result in the finite case where you have a boundary term, which is actually, it's long to write, but it's not that complicated. It involves the Green's function at the boundary, between inner point and boundary point. Okay, so what does this result tell you? Okay, so the first thing is that, well,
Can you just say, again, just to make sure I get it and everyone gets it, what's the generality of this result? So any isoradiograph.
Z-invariant, so critical or non-critical, so you have a full regime. So the assumption is that it is Z-invariant, meaning that you choose the coupling constant 1/2 log 1 plus Sn over Cn. Okay? And so using these coupling constants, when k squared ranges from -infinity to 1, you span the whole range 0 to plus infinity for the coupling constant, and when k is equal to 0, you recover the critical case.
Okay, and then what you recover here is explicit formulas for this Castellan inverse.
Yes, so for Ising, for contour probability, for the low temperature, for the contour representation of the Ising model, okay, using this Fisher correspondence, this means that you recover local formulas for, such formulas, you can compute any edge, any contour edge probability in the Ising model.
So you give me, so in the dimer model, you know for any finite collection of edges, the probability that they're there.
Yeah.
And for this model, so you have explicit formulas for
the Ising model using this massive Green's function.
For all your Ising model properties, okay.
Ising model probabilities using the random walk Green's function, where the random walk lives on the same graph as the Ising model, in the finite and infinite case.
Right, and this doesn't work for all non-bipartite
Fisher graph.
Fisher graphs?
No.
It's just for the ones from this isoradial story.
Yeah. So now we're thinking with Dima about his S embeddings. So things might work out.
But the upshot then is that you understand the Ising model generally much better on these graphs.
Yeah. Well, for the moment, yeah. So there are deep reasons for that. I think that this locality, the invariance property, tells you that your model is local in some sense. But I don't use this when proving these identities. But sometimes, things work out that I think it's important. But then if you have these S embeddings, you kind of still have this Z-invariance locality property. So it might be that you can extend it, but you lose a lot of symmetry. So it's not, it requires work, but it might be that it extends. It's the right framework. What I would say is that it's maybe S embeddings is maybe the right framework to see any Ising model embedded rightly so that you can see the real structure coming out.
Now,
this is what I believe.
In this embedding, do you expect that it's, conformally invariant, that these...
Well, Dima is proving that.
Dima's proving that.
Yes.
Okay. I see. So this is part of that whole project.
Well, no, this was before the S embeddings.
Okay.
Okay? So I finished that. I didn't know about S embeddings, but even had I known, first, it's really quite intricate, so I think you still first need to really understand the isoradial case and then maybe go to S embeddings.
Okay.
Okay? So yeah, so what does this tell you? so that the Boltzmann or Gibbs measures of finite infinite volume are expressed as a function of the massive Green's function. So this is what I just told you of this killed random walk. So the random walk is killed when you're away from criticality, or also as a function of the Z-Dirac operator using well-chosen values of U. So this is kind of reminiscent of a result by Marcin, where he has a non-backtracking random walk representation, where these non-backtracking random walks, if I understand correctly, come from this, what he said, his Markov matrix arising from the Katz-Ward matrix. But here we have real random walks on the usual graph. They're not special in any way, except along the boundary. Now, another important point, which was also part of the motivation, is that this specific coefficient, so this one, okay, is the fermionic spinor observable of Kadanoff and Seva. So it's what you get if you put a neighboring order and this order operator. And this has been, so the fact that this coefficient of the Castellet matrix is this operator is an observation due to Dubeda in his paper Exact Bosonization of the, I don't know, can't remember, well, bosonization paper. Okay, and so this is the observable. It was phrased differently, but it's the observable used by Smirnov first, and then Chelkak and Smirnov to prove conformal invariance of the Z-invariant critical Ising model. And so the idea there was so they don't have an explicit expression for the observable. What they use is local relations, so this S holomorphicity condition, and then a boundary value problem. And to handle this, they integrate the square of the observable and prove that it's subharmonic, superharmonic, and then this allows them to prove convergence. And so the point of this result is actually you can understand that finally they're observable. If you look at this at criticality, you can see that they're observable, while the f function in their paper is actually this difference of Green's function. Okay? You can recover, and then this is kind of this projection thing phrased out. Well, you can like kind of relate the two. So this formula shows that actually everything already holds in the discrete and not only in the continuum limit. And also, the thing about this result is that it shows that it holds for the full Z-invariant regime, as I just told you. Okay, now, so at criticality, you have a real derivative of a Green's function, so you converge to this phi prime of a harmonic function, and away from criticality, you have kind of a twisted derivative. Now, it doesn't, I mean, I talked to Dima about it. It doesn't make the convergence any easier, okay? It's not like a miraculous tool, but I think it really shows the underlying structure that holds in the discrete and why you should have this convergence in the continuum.
So why do you say it doesn't make convergence easier?
Well, because Dima told me that analyzing this Green's function, so I haven't tried, I'm not going to because it's done, but Dima told me that analyzing this Green's function, well, you have the boundary term, but I believe it's not too bad, but you still have to, you don't see it because it's a full plane version, but you have a finite version. And understanding, I mean, the boundary conditions are quite tricky. Like, I mean, they're probably the same as they have, but you know, it's sometimes difficult to see. But for you have this tangent condition, so it's not going to be easier. I don't know, because he told me that when integrating the square, it makes things kind of easy, more easy than just directly considering the observable. But this, I haven't, tried it, so I'm just rephrasing what he's saying.
I'm speaking very naively that.
Yeah, naively, I think
to reduce this to Green's functions are much easier than the Ising model, from my naive point of view.
Well, from my naive point of view, but he did all the thing, and so I believe in his point of view, right? Okay. So yeah, and so it extends to the full Z-invariant case. So I think some of you are interested in working out, you can take this near massive limit. So I think some of you are working on that. So let me advertise that this is maybe a good starting point, because you have taking this near massive limit amounts to taking k squared converging to 0 at the right speed, and then you probably can come out with the formulas quite rapidly from this formula, even handling the boundary condition. Okay, away from criticality, this also explains the occurrence of large deviation estimates for the killed random walk and spin correlations of the supercritical Ising model. So this was a result. It's not a proof, it just explains, but then you don't want to do the work again because it's been done. But Reda Messick, so he left research, but we're PhD together. He told me, there's a random walk in the Ising model. I know. And so he had this observation that if you computed a supercritical Ising model correlations, then you had large deviation estimates of the killed random walk. And this result was later on proved by Beffara and Duminil-Copin. And actually, this is what Marcin said, not completely heuristically, but when you're in the supercritical regime, the spin correlations are well approximated by this Castellane inverse, okay? Away from criticality, at criticality is certainly not the case, you have a completely different behavior, but at supercritical regime. So then once you know that you directly have a Green's function, it kind of tells you why you should have these estimates. And actually the killed random walk is exactly the one that you get from our massive Laplacian. Well, for Z2, this is done for Z2, but if you specify to Z2, this is what you get. And so the proof that we propose here is not combinatorial, but it unifies the results for the partition function and for probability measures. So, so I have a few minutes to tell you about the proof. So the idea of the proof is quite easy, is you want to relate all of these Castellane matrices in such a way that you can have conclusions about determinants and inverses. So then it's a lot of work. So there are 3 steps. So the first step consists in considering the Castellane matrix on the Fisher graph and the one on a bipartite graph, okay? Which I have not introduced and I will not today. And so this part has been mostly done by Julien Dubeda. He has a nice matrix relation. Anyway, for determinants, for going to the inverse, I must admit there was some quite involved, technical work to go to inverse matrices. But anyway, he really had the basis of this step. And this step holds for all planar Ising models. You don't need this Z-invariance thing. Then a second step is to relate the Castellane matrix on this graph to the one on the double, so this Zu-Dirac operator. So this is like the most difficult, this is what was missing to me for a really long time. And also this one actually, because I didn't have this operator. And then you have to relate the Zu-Dirac operator to the massive one. So these directed pair of spanning trees to rooted spanning trees. Okay, so let me start with the third step. So the third step is Dirac and massive Laplacian. So what I prove is the following identity, that for every u in this real locus of the torus, you have the following identity between the Dirac. So it's like the Dirac relation, dd bar equal Laplacian, but it's a massive version of this relation. And so here you also have u on the left, you don't have it on the right, but you kind of see that it's trigonometric identities. Okay, and in the finite case, so this was if you want to go infinite, it's easy to go to inverse. Okay, but in the finite, it was quite difficult to have a 0 here, and you want to have a 0 here because otherwise, when you go to inverse, formulas get messy. So this is where you have this u coming along the boundary. Here you don't have a u, and then you have this matrix Q. Okay, so this is the Ising version of the. This is for the specific Ising model boundary conditions. If you do it with normal boundary condition, you don't have this Q. And so, important remark, when k is equal to 0, this is a result of Kenyon with relating the Dirac operator to the Laplacian without mass operator. And so using these relations, you can, as I told you, I show you for the infinite case, but you can do it for the finite case. You can recover formula for inverse coefficients. Okay, you go, this is in the matrix form, this is in coefficients form. And so what this tells you is that for every u, you have an explicit formula for the inverse of the ku operator. Oh yeah, I haven't told you that actually this weight function for this Zu-Dirac operator is positive. Dn is always positive. So it's really a statistical mechanics model. Okay, you wouldn't want to have negative weights. So a remark is that this allows you to, just forgetting about Ising, it allows to compute the measure on directed tree pairs via the massive Green's function. Okay, and this is not clear a priori. And this, in the case of Z2, was he doesn't use the Z-invariant weights, but still you can recover them, and it was proved by Chita Sunil in 2011. Okay, and then you have to go to determinants. So let me show you, just go back. So if you want to take determinants, you will know that the square of this determinant is equal to the product of these two, okay? But when you're away from, well, when you're in the massive case, rooted spanning forest and its dual one have nothing to do, okay? So it doesn't tell you why one of them should be equal to one of these determinants. So this needs additional work. And so this is this theorem to show that actually the directed spanning trees partition function is equal to the rooted spanning forest partition function. So in the case equal to 0, as I told you, this is the temporally bijection. And then in the other regime, you have to use gauge transformations on your matrices. So first, for bipartite graphs, this is quite a classical tool. And also, you can also use gauge transformation on non-bipartite graphs. And so, well, yeah, you have. And then once you have done these two steps, you still use the Kenyon-Prop-Wilson temporally bijection, and then you can conclude. So this is how to relate the Dirac and the massive Laplacian operator. Now the key point is KQ and the Dirac. So there you have a relation like this. So this is the relation. T and S are of course explicit, and then you have a version for the Ising boundary condition finite case. So the problem with this relation, which stuck me for a long time, is that these matrices are rectangular. T and S are rectangular matrices. So you cannot go to inverses so easily. Well, you cannot. I mean, you have to do something else. So when you go, well, you can do inverses, but you cannot invert these two matrices, okay? But what you get is inverting KQ and K, you obtain such a relation, okay? And so you have a relation between linear combinations of coefficients and linear combinations of coefficients. And so you can make it explicit. This is just the explicit version of S. Well, this is the definition of S, so it's all elliptic functions. And so I thought, well, before I didn't have the U, and I said, okay, this is nice, a linear relation, but it doesn't suffice to extract the coefficient. And then I was able to put the U inside to have a more general family, and then I realized that just by specifying some values of U, well, you can extract coefficients because you can cancel one, and so you can, because our goal is to extract one coefficient, and well, by specifying U, you can do that, okay? And so once you have this dependence in U, which is kind of annoying for some things, then actually it helps for the other things and gives you this way of extracting coefficients. And then to go to the determinant, so this is the KQ, the T rectangular, S, and then the K Laplacian. So you can easily get a relation like this. But then what you want to compare is this determinant to this one, okay? And there it's difficult because if you first, it involves partitioning the vertices, but I will be quick. You have to partition the vertices, and if you don't do it right, then you just have 0 equal to 0, okay? So you have to partition them in a nice combinatorial way, and then the proof is reminiscent of the combinatorial one, and then you have to compute these determinants, which are not easy, but once you have a combinatorial interpretation, you can recover results for the determinant. And this is, so the last step by Dubédas, so this is Dubédas matrix relation between KQ and KF. And then, well, you can go to inverse, so you can exactly, so this bipartite Ising model has all the information actually for this Fisher. So actually what this tells is that actually you can completely handle the Ising model probabilities using this bipartite diamond model, which was kind of implicit in Julien's paper using bosonization identity, but here the operators are really directly related. And well, so it's also related to the sixth vertex. And then a funny observation is that when the coupling constants are negative, which you're allowed to do, then you have an anti-ferromagnetic Ising model. Then you also have this bipartite dimer model, but some edge weights become negative. Okay, but still, so it kind of justifies to maybe study bipartite dimer models with negative weights. I don't know. And so let me thank you, and just I will do some advertisement. So I asked Adrien, do you think it's okay? I'm not making money on this, so I'm not making any money. It's just a conference we're organizing with Cédric and Kylian in December, so we'll be glad if you could come. And I thank you.
Any questions?
Just one light question. You have a constraint on the mass when you look at the massive Laplacian.
Yes.
I don't see what it is in the discrete. What kind of massive Laplacian are you discretizing in the continuum?
So okay, so when you take so probably when you take the mass going to 0 and you take the right scaling limit, then in the continuum you just have the usual massive Green function with mass 1 if you renormalize appropriately. And you have, because then if you take the limit going to 0 at the right speed, then you have you recover rotational invariance, and then you get
But when you are away from 0,
yes,
you have
a continuous analog away from 0. No, it's only because if you want to recover, well, from what I understand, if you want to recover a continuous analog, you still need to have this rotational invariance, and this you recover only in the near critical regime.
so it's just it's a way of being near critical.
Well,
The continuum, you don't see it anymore, right? Like, this is your claim?
my claim is that the formulas hold all the time, but if you want to find see something in the continuum, you have to look at this near critical regime, because then in this critical regime you can recover, and this we have done with Kylian and Cédric. You recover the asymptotics, and you see that they become rotationally invariant, and then if you scale it properly, the mass converges to 1, and you recover a massive Green function. And otherwise, it's okay. I don't know.
Several times you said you have local expression. What do you mean by local expression?
Okay, I often say local for many different reasons, so
That's the point of my question.
okay, so when I say local for the inverse, I mean that when you have this linear combination, it just involves the starting and the ending vertex. The linear combination don't need the whole graph, you just need an information at the beginning, at the end, and this was the meaning of local for these inverse expressions. Then I talked about our results with Cédric and Kylian for local expressions. So this is something, well, it's not exactly, it's because we have a way of computing inverses using a contour interval which uses an observable which depends on the path only and not on the whole graph. So you always have this local means that you don't have the whole structure that it gets involved, but for maybe in a different way, not for the same reasons.
In the continuum, mass transforms conformally covariantly, right? So can you get like spatial variance in the discrete Z-invariance, Z-invariant weights?
You mean spatial variance like
Well, different mass at different points. Because in the continuum, you can get non-constant mass just by looking at it under a conformal transformation.
I'm not sure I understand your question. So do you mean like computing the variance, you mean like going towards a Gaussian free field or something like this, or it's not this at all? Because this we have looked at. So this I can answer, but I don't know if that's your question.
I'm just saying that if you map the massive Laplacian operator in the continuum under a conformal map, you get a non-constant mass, right? Just multiplied by the normal.
Okay, and can you see this? Well, we haven't tried, but probably also taking this near critical regime, you should be able to see it using the continuum analog of the Green's function, where you probably know exactly what happens. So you should be using, it's all, to see all of this kind of things, you have to take the limit k squared equal to 0, and then probably use the continuum limit.
Okay. Any other questions? All right. Well, let's break for lunch. Thank you.